Well, welcome to the afternoon session. My name is Standa Shivni. I'm based in Oxford, and I've recently taken over from Prudence as the chair of the LMS Computer Science Committee. So, and I have the pleasure to introduce the next speaker. So, Dr. Angeliki Koutsoukou-Argyraki, sorry for butchering your name, has done 3 degrees in mathematics in 3 different countries, if I got it right, Greece, Denmark, Germany, and after a few years at Cambridge is now a lecturer at the Royal Holloway in London, and will tell us about verification in theory and practice.
Okay, thank you very much for the nice introduction. Thank you very much for having me. It's great to be here, and thank you for the great organization. So to introduce myself, I did my PhD in pure mathematics, pen and paper mathematics, in logic and nonlinear analysis. Actually in applied proof theory, so applications of proof theory in various areas of nonlinear analysis. And my work in verification, so after my PhD in pure math, I moved to verification. So my work in verification involves the formalization of mathematics using Isabelle HOL. So I worked as a postdoctoral researcher within Larry Paulson's Alexandria project. It was a big European big project funded by the ERC. At the University of Cambridge for 6 years. So Alexandria finished in the end of August, and the past couple of months, since the 1st of September, I've been a lecturer at Royal Holloway in computer science. So I apologize for the oversimplification of this sketch. So my point is mathematics and computer science, of course, intersecting. This is an oversimplification, of course. And verification, seeing this as an area of computer science, of course. My own work focuses on formalizing mathematics in particular, not software or algorithms, but proofs in pure mathematics. So I've drawn a small pink arrow back to mathematics, signifying this cross-fertilization, right? So my plan for this talk is it will be a brief, quite general discussion. It will be a non-technical talk. It will be a brief discussion on the state of the art and the potential of the area of formalizing mathematics with proof assistance. I will talk about some highlights, choosing some highlights, selected pointers on formalization work, and some tips on getting started with Isabelle for interested people. So going back to the 90s, the QED manifesto, it was a very optimistic grant proposal for a central computer-based library of all known mathematics, fully formalized and formally verified. By that, meaning automatically checked by computers, right? So here is the paper from 1994. So this project was considered to be, well, it was not considered to be a success. It was soon abandoned. However, or really was it? Because nowadays, we've seen a big revival. So formalization of mathematics with proof assistance is an area that is becoming more and more popular. So nowadays, we have big, extensive libraries of formalized mathematics available in many different proof assistants. So we have MathLib, Lean's library, and the archive of formal proofs by Isabelle, and many more. Of course, there is a variety of proof assistants available based on different logical formalisms. Right. So why formalize mathematics? Usually when I give these general talks, I like to start with my own personal motivation, starting from my research work during my PhD. So this is where my interest was stemming from, right? So because I worked in applied proof theory during my PhD in proof mining, which involved pen and paper extraction of constructive information from proofs in the form of computable bounds. And in my own research work, I encountered situations where I had proofs, different proofs of the same statement, giving, of course, different computational content. Of course, this led me to see something happening. This led me to questions about the nature of proofs, and in particular, what is it that makes a good proof? And of course, there are many possible answers to this question. It looks like it's stuck.
So I was just starting the video. Sorry to have interrupted. It's quite a big file, so that's why it's very slow. Okay, so just bear with me.
Right. Okay. So I'm saying there are many possible questions to what we mean by good proof or better proof. Proof that is shorter, more elegant, and simpler proof, considering Hilbert's 24th problem, the secret last problem from Hilbert's list. Find criteria for simplicity of proofs, or to show that certain proofs are simpler than any other. Of course, these things call for a very long philosophical discussion in terms of reverse mathematics. We can think of a better proof as a proof in a weaker subsystem of second-order arithmetic. And interdisciplinary proof, if we have a proof that, let's say, a geometric proof for an algebraic statement, or vice versa, it would be considered to give a deeper mathematical insight. Or a proof that is easier to reuse. So if it involves some algorithm or technique or some intermediate result that can be recycled using different contexts, that would be a measure of how interesting or how good a proof is. So these are different points of view. Or a proof giving better computational content, again, referring back to my work in proof mining. Of course, better computational content can also mean a lot of different things. And my thinking was that formalization could give us insights on these questions on the nature of proofs. So that was my original motivation, but of course there are many reasons why we formalize mathematics. Of course, starting with verification, the need to eliminate mathematical mistakes. And we have the famous example of Vladimir Voevodsky, who started working in formalization himself after discovering errors in his own work. And this is a paper by Voevodsky from 2014. Sadly, he passed away in 2017. In this paper, he outlines his personal journey, how he got interested in formalization after he discovered errors in his work. So verification is, of course, a big reason. And I'd like to refer to this very insightful paper by Lambert from almost 10 years ago, where again he argues for the need for exactness in the way we write mathematics and write mathematics in a formal language. But of course, there are many, many reasons beyond verification, right? Hence the subtitle of my talk today. Well, again, something which is indeed related to verification is, of course, reviewing. So many people imagine that in the future, formalizing mathematics with proof assistance would be would facilitate, would speed up the reviewing process. So submitting, whenever we submit new results to a journal, we will submit the proof formalized in some proof assistant. So this would make the reviewing process more reliable and faster. But then there are other reasons. So preserving mathematical knowledge in big libraries of formalized mathematics, this means that we are creating databases with an enormous potential for the creation of future AI tools that could assist mathematicians in many different ways in their discovery or invention, whatever you prefer, of new results. So when you have proofs written in code, code is something alive. You can modify it, you can recycle it, you can remove a lemma, see where the proof breaks. So this gives you more insights into proof, of course. So this opens the door to a huge area of possibilities, right? When you have your proofs written in code instead of pen and paper. It's again stuck. Okay, right. So I like to think of the computer as a magic mirror when you're formalizing mathematics, because it can lead to deeper, formalized mathematics can lead to deeper understanding of a proof and new insights. So even material that is already familiar, it can be seen in new light when using new tools, right? And because when we formalize mathematics with a proof assistant, we need to look at the proof at a very, very high level of detail. This forces us to think and rethink proofs and definitions from different points of view, from different angles. So formalizing can help with a deeper understanding of the proof. So related to that, formalizing a proof with a proof assistant can be a way of keeping track of all the details of the complicated proof in a sort of bookkeeping way. So this is an extract from Kevin Buzzard's blog here. That was a guest post by Peter Scholze, commenting on the work on the liquid tensor experiment, which involved formalization of some work of his in the proof assistant Lean. So he says that the Lean proof assistant was really that, an assistant in navigating through the thick junk that this proof is. So he says it was not easy to keep all the objects of the proof in his memory, and therefore Lean was sort of a compass to guide you through the proof. And with the help of Lean, one could see a couple of steps ahead, formalize those, proceed to the next step, and also help with seeing the next step in the proof, but also seeing the bigger picture. So how each part of the proof interconnects with the rest. And for Lean in particular, there is a blueprint tool developed by Patrick Masson that it shows the interdependency of proof parts, and it also tracks the formalization process, which is extremely useful for Lean users. Of course, proof assistants can also be used as educational tools for all the reasons already mentioned. And at all levels, actually, in my opinion, for high school students, for university students, but also for more elementary mathematics, proof assistants could be useful for learning because you get immediate feedback from the proof assistant about your proof, where something goes wrong. Especially for Isabelle, for example, we have a counter-example finding tool, for instance. But even without counter-example finding tools, they can be very useful. And last but not least, it is fulfilling and fun. So I see students have a lot of fun learning how to use proof assistants. It's a bit addictive, a bit like a computer game. So a vision for the future of research mathematics is to create an interactive assistant that would help research mathematicians in their creative work by providing brainstorming and hints, proof recommendations, counterexamples, proofs of auxiliary lemmas, intermediate steps, suggesting conjectures, providing information on relevant literature results, helping with bookkeeping, and formally verifying the new results. So the goal for our future vision is to assist mathematicians, not replace them. And this is a vision described by Timothy Gowers in this paper, which is already several years old. So he describes how a dialogue between a user and a computer would ideally look like in the future to interactively assist the human to arrive at new conclusions. And maybe we're getting there now with large language models. There's some experimental work hinting that we might be getting closer to a vision like this. So I really like this citation by Barndrich and Bittig. It is again, I cannot see the date, but it's maybe around 10 to 15 years old already.
Shall I move the...
That's fine. You can move it a bit to see the exact date, but it should be around 10 years old at least, this paper. So they say that we believe that when later generations look back at the development of mathematics, one will recognize 4 important steps. The Egyptian, Babylonian, Chinese phase in which correct computations were made without proofs. The ancient Greeks with the development of proof. The end of the 19th century where mathematics became rigorous. And the present where mathematics supported by computer finally becomes fully precise and fully transparent. And by the way, I have actually drawn a little question mark here because now there is a lot of discussion that, arises from the developments in AI, because as mathematicians, we need understanding. We don't fully precise, yes, but fully transparent. Now it's a question with automation that is so powerful that makes it difficult for us to reconstruct how the proof was created, where it came from. So maybe this defies the actual purpose. So let's see. It's a very big topic for discussion, right? So, it seems like we are perhaps towards a new era in mathematics. We have seen a big shift. Until recently, formalization was an area of computer science, but now it is quickly attracting the interest of working mathematicians as well. There are lots of enthusiastic online communities emerging, lots of tools like Zulip that enable massive collaboration, massive collaborative projects. Libraries of formal proofs are expanding at an increasingly high pace. And there are lots of student-run projects emerging as well. These are very welcoming, positive communities. Everyone is welcome to join. Very helpful towards new members. So if you could move the bar, that would be great. So I can see the best.
Very finicky. Just give me a minute.
Yeah, but I don't want to be late. So another. So a couple of hints that perhaps we're moving towards a new era in mathematics is that Land's mathematics subject classification includes for the first time subject classes on the formalization of mathematics. So now mathematics is recognized, formalizing mathematics is recognized as a research area in mathematics as well, in addition to an area of computer science. So that was quite recent, and it's a big thing actually. And yes, at the 2022 International Congress of Mathematicians, Kevin Buzzard here and Georges Gontier, so two big figures in the formalization of mathematics, they were invited to speak at this big event about the formalization of mathematics. So it looks like there is so trends are shifting a bit, I think. Some people are nodding, so
I'm hoping.
yes. It's still a bit stuck. Okay, so right. I want to refer to some milestones in the area, and my apologies if I've missed any important ones, which I'm sure I have. So I would like to start by referring to the formalization of the proof of the four-color theorem in Koch by Koutsoukou-Argyraki in 2008. He also formalized the Phi-Thompson proof of the odd order theorem in Koch again. This was a very big project by Hales, the Flyspec project. So he initiated a very big effort to formalize in HOL and Isabelle HOL the proof of his famous proof of the sphere parking problem, the Kepler conjecture. So the reviewers could not confirm that the proof was actually correct. So he decided, okay, I will verify this. It took about over 10 years, right? It was the so-called Flyspec project, so a very big initiative that was successful, and it shows the potential of proof assistance for actually indeed verifying mathematics, right? Pure mathematics. Larry Paulson formalized the adder's incompleteness theorems around 10 years ago. An irrationality proof of the Riemann zeta function by Appert was formalized in Koch by a team in France. Jacques Magoubi, you can see. The proof that the Lorentz attractor is chaotic was formalized by Fabian Imler in 2015. A very famous, more recent project was formalization of Scholz's perfectoid spaces in Lean by Buzzard, Comelin, and so on. Grothendieck schemes in Lean were formalized again by a group led by Kevin Buzzard, and they were also independently done in Isabelle HOL by some of my colleagues at Cambridge. A substantial amount of material analytic number theory in Isabelle HOL has been formalized by Manuel Eber. The independence of the continuum hypothesis, again, we have this both in Lean and Isabelle ZF this time. It stands for Zermelo-Frankel. This was done again quite recently, 2021 and 2022 for the Isabelle group. The formalization of the solution to the cup-set problem, a problem in combinatorics, was again done by a group by Yamen, Holz, and Lewis in the proof assistant Lean in 2019. I'd like to mention this project as well. So Meredith's regularity lemma and Roth's theorem on arithmetic progressions were done in Isabelle Hall by Paulson and Edmonds, who is his PhD student, and myself, Cambridge. And it was done independently, considered at the very same time, in Lean by Dillis and Mehta. I want to say a few things about this project, just the basic idea. So this is the reference to our paper, and our entries, these are our AFP entries from 2021 with Chelsea and Larry Paulson. And the sources we used were the book by Tsao and some notes from a course by Gowers. So the Lean group used a different source, by the way. And we also have a chapter in our paper comparing a bit the formalizations and discussing a bit about the comparison. So I'm just giving here, yes, the definition of the upper asymptotic density for the sake of completeness. So Roth's theorem is a special case of the Meredith's theorem, which is essentially an answer to a null conjecture by Erdos and Turan. So the Meredith's theorem was proved in 1975. It says that every set of integers with positive upper asymptotic density contains a k-term arithmetic progression for every k. So Roth's theorem proved in 1953. And by the way, the original proof was done in an analytic way. It was based on Fourier analysis. This was not the proof we followed. By the way, we followed a combinatorial argument. I will come to that. So Roth's theorem is a special case of Semeredi, and it says that every subset of the integers with positive upper asymptotic density contains a 3-term arithmetic progression. So it's a special case for k equals 3. And this is how the statement looks like in Isabelle. And here I'm including a few definitions, a few graph theoretic definitions. Like I said, our group was graph theoretic, combinatorial. So I'm explaining here the definition for the edge density between two subsets x and y, which are sets of vertices in a graph. Right? And the definition of, actually, where I'm getting to all of this is the definition of an epsilon regular partition, right? For that, we need the epsilon regular pair definition. So I'm leaving the definitions a bit here for you to look at. And now I will show you Semeredith's regularity lemma, which attests that for every epsilon there exists a constant m, such that every graph has an epsilon regular partition of its vertex set into at most m parts. So it gives a sense of randomness for graphs, in a sense. And this is how our formalization looks like in Isabelle Hall. Now, Semeredith's regularity lemma was used to prove some results in extremal graph theory that were eventually used for the proof of Roth's theorem, right? Because for Roth's theorem, we used a combinatorial proof, follow the combinatorial proof. So to this end, we proved the triangle counting lemma that follows from Semeredith's regularity lemma. So this is the statement. So these are fundamental results in extremal graph theory, and they are also used in many different contexts, right? So assuming we have these irregular pairs for some epsilon, assuming that, so I'm just reminding you the definitions, the edge density, right, is this. Assuming we have this assumption for the edge density. Essentially, what we're doing, we're counting triangles. So we have the number of triples, x, y, z, in this, where x, y, z are respectively in these big subsets, such that x, y, and z, little x, y, z form a triangle is at least this big, right? So it is an estimate for the number of triangles we have in a graph. And this is how the statement looks like in Isabelle, the way we formalized it. And this is a triangle removal lemma that says how we can make sure that we can make a graph, any graph on n vertices, triangle free, right? So for all epsilon, for all positive epsilon, there exists a delta such that any graph on n many vertices with less than or equal to delta times n the cube triangles can be made triangle free by removing at most this many edges. Okay, and this is our formalization in Isabelle. Now I'm coming back to giving you milestones and recent advances in formalizing mathematics. So the sphere version project was an important development by Massow, Van Loon and Nash, HOL and Lean. Meta recently formalized in Lean result by Campos, Griffiths, Morris and Sahasrabudhe on an exponential improvement to the upper bound on Ramsey numbers. A year before, Meta had formalized together with Bloom in Lean a paper by Bloom on unit fractions, actually a very recent paper, a combinatorial paper. This is not working, but it's okay. It's working again. Great. And I would like to mention our formalization of the Balogh-Zemurelli-Gowers theorem in Isabelle Hall by Chelsea again and Mandas. We went together in Cambridge to formalize this big result. So a few basic definitions. So as you can see, this is a very simple concept. The concept of a subset. So given A and B, finite subsets of an abelian group, this is what we mean by the subset. So we take the set of all possible sums, right? And the different set is defined in the same way. And for n many copies of A, we denote this way. And I would like to quickly define the notion of the additive energy. To this end, we need the notion of an additive quadruple in G, which is a quadruple such that this condition is fulfilled. And the additive energy of the subset A of G is the number of additive quadruples in 4 copies of A, right, divided by the cardinality of A to the cube. So this is the reference to our paper. So even though the basic notions are very, very simple, so this is a very profound result in additive combinatorics, and it played a central role in Gauss's proof deriving the first effective bounds for Zemurelli's theorem, which is the theorem I mentioned in the beginning on arithmetic progressions. So Balogh and Zemurelli had proved in '94 that every finite subset of an abelian group of given additive energy must contain a large subset if the subset is small. And Gowers, a few years later, gave a new proof with better bounds on the cardinalities. So this is the statement, right? We have a subset A, a finite subset A of an abelian group, and with a given additive energy, then A has a subset A prime, which has a big cardinality, but its difference set is small. There is actually an analogous version of the theorem for some sets and for different sets. So both of these work and formalize both of them to just a symmetric argument, right? And what is interesting is that the proof involves an interplay between different areas of mathematics, graph theory, probability theory, and additive combinatorics. And we were able to express this interplay via locales, which is Isabelle's module system. And to this end, we also used a new general and elective graph theory by Chelsea and Mons. Now back to milestones. I would like to mention that there is significant student activity. I would like to mention again Kevin Buzzard's very vibrant London Lean community at Imperial College London. So thanks to Kevin, there is this huge, wonderful community of very enthusiastic students working in Lean. I would like to mention this case of a project that was designed and by students and executed by students, a group of students from Germany. They formalized in Isabelle Hall Matyasevic's famous proof of the DPRM theorem that says that every recursively enumerable set of natural numbers is the HOL and Lean, which gives a negative solution to Hilbert's tenth problem of the recurse, right? So this is the AFP entry. So I'd like to mention this because it's interesting that students take this initiative and it shows how things are shifting, like I was saying, right?
Does Matthew say it's involved in the?
There was, I think who? There's Jonas who.
Matthew said
Yes,
he
he worked with this, so he said they worked directly together, and they told me that he went to the university and he gave a talk, and then they started talking, and then they decided to do it together. But it was the students' initiative, and he was very interested as well. So they did it. Yeah, he was himself involved. So this is his name on the AFP. Of course, the liquid tensor experiment is a very big success story for the formalization of mathematics. So condensed mathematics is an area introduced by Clausen and Schulze. They introduced condensed sets, which is an alternative notion to topological spaces. And in late 2020, Schulze posed a formalization challenge on Kevin Buzzard's blog, the Xena project blog. And the Lean community took up the challenge. So a huge collaborative effort started, and I don't know how many people were involved, more than 10 people. It was led by Comelin, but there were, like I said, many people involved. There are lots of references online about that. And finally, the project was finalized in July 2022. And this has attracted a lot of publicity. There was an article in Quantum magazine in 2021, it was actually shortly before the end of the project, and also in Nature, right? So this has attracted a lot of enthusiasm. And now some important developments coming up. So I'm very excited about Kevin Buzzard's project. He is starting a 5-year project to formalize in Lean Fermat's last theorem, or at least a big portion of the mathematics involved in the proof. And this is a very recent development. So a very recent paper that was published, I mean, the preprint was announced recently, is the new proof by Gowers, Dean, Manners, and Tao of a conjecture proposed by Katalin Marton, known as the polynomial Freiman-Ruza conjecture, which is a theorem in combinatorics and number theory. So Terence Tao announced recently, a couple of weeks ago, that he's going to formalize this proof in Lean together with Dilys and Mehta, who are both students. Mehta is finishing his PhD. Dilys and Mehta were also the authors of Roth's theorem and Semeredis' regularity lemma in Lean, right? And it looks like they have made substantial progress already. I have seen the progress graph from Patrick Massoud's tool, and it looks like it's evolving. So it is really exciting to see this. I would like to say a few words about the Alexandria project at Cambridge. That was the project I was involved in for 6 years. So it was led by Professor Paulson, and I'm just giving you the link to the project here where you can find all relevant information and the work produced. So our goals were to expand the body of formalized material on the archive of formal proofs and the Isabelle libraries. We worked on case studies to explore the limits of formalization. We developed tools for managing large bodies of formal mathematical knowledge. For example, we have made a search engine. And also another part of the project was automated and semi-automated environments and tools to aid working mathematicians. And I'm just going to refer to Larry Paulson's paper from Colloquium 2023 that was published a couple of months ago from the International Conference on Intelligent Computer Mathematics. So he gave an invited talk, and this paper contains an outline of what we achieved in the project. So I'm just giving this reference for now. And some references to my contributions within Alexandria. I didn't want to give a technical talk on my work today, But I'm just giving you these references. So I gave 2 recent talks that were much more technical than the talk today, where I talked about my contributions, or at least I gave some references to them and a bit more detail. So my line of work, together with colleagues, I initiated this line of work in additive combinatorics, and we formalized a lot of material together with colleagues. So I give all the reference on that in this paper, which is the paper for my invited talk in the proceedings of ITP from last August. And also I gave I gave a couple of tutorials in summer school in Germany, interactions of proof assistance and mathematics. It was an online, I gave my talks online, I wasn't there, unfortunately, but you can look up my slides and you can see some more references to my work within Alexandria. So I was going to give a very, very quick, brief introduction to Isabelle. Of course, some people here are already experts in Isabelle. I was thinking I should maybe say a few things for interested people who would like to get started. So it was developed by Paulson, Nipkow, and Wenzel, starting from the late 1980s. Isabelle HOL is based on higher order logic, and it is built on simple types. There is a big emphasis on producing proofs that are structured and easy to read, using the ISAR proof language. And a very big bonus is that it features sufficient automation. So Sledgehammer that calls a bunch of external interactive theorem provers. And there are also counter-example finding tools like nitpick and BigCheck. So I use Sledgehammer a lot myself. I find it very useful. This is the main website where you can download and install the software, and also you can find lots of documentation. The Isabelle manuals are there. The installation is very easy and straightforward. So this is the main website. Of course, whenever you download Isabelle, it comes together with all the libraries. The library is not the archive of formal proofs. I will come to the archive of formal proofs. But you can also access the libraries online. So for example, Isabelle HOL, these are the libraries. This is the link, and that's what shows here. For example, if you click on the analysis library, again, you have a lot of theories in analysis, let's say. And there are also dependency graphs. So if you click here on the theory dependencies, you can see the dependency graph. It's actually quite massive. It goes a long way down. This is just the start of it. So it's not the whole analysis library, but just to give you a taste of how it looks like, it goes all the way down, which is actually quite interesting and useful to see, especially if you want to try organizing or reorganizing the library a bit, which I was doing for some time, for the analysis library in particular. And this is an example of a structured proof in Isabelle HOL. It comes from theory Weierstrass theorems. And this is a statement that just says that if we have a polynomial function, right, defined in this way, then we can always, this shows that we can always find a vector derivative at every point, which is also polynomial, which is also a polynomial function, yeah? So this is how the proof looks like. Just to give you a taste of how a structured proof looks like with Isabelle. Like you have proof blocks, right? And in my opinion, it's quite user-friendly. So I already mentioned the archive of formal proofs a few times. It is a big collection of proof libraries written in Isabelle. This is a recent screenshot. You can see Manuel Ebert has a bunch of very impressive recent entries here. You can browse the archive of formal proofs. There is a search tool as well, where you can search for material. Just to show you the statistics of it. So it is already almost 20 years old, started in 2004. It is really a vast collection of formalized material, but not all of it is mathematics, right? A big chunk is computer science and logic. As of 27th of November, there were 784 and 87 entries by 470 authors, right? And it keeps growing. So if you go to statistics here, you will be able to see classification of the formalized material by topic as well. Oh no, sorry, not just, if you go to topics, sorry. So topics gives a classification according to different topics in mathematics and also subfields of mathematics. And this is a search engine that I built together with my colleague, Yanos Stathopoulos, who is an expert in natural language processing. It's a concept-oriented search engine. It works only for the 2021 libraries and archival formal proofs, unfortunately, but we're going to get it dated. And we also have a YouTube channel where it's just for the search engine, where we have a couple of demo videos to explain how it works, how you can make the best use of it, if you'd like to explore it. And if you're interested in trying out Isabelle, there's a lot of help online. This page contains a collection of quick access links that are helpful. So the Isabelle mailing list is very helpful to subscribe. You will get an almost immediate answer to most of your questions. Right, it's very useful for beginners. The Zulip chat as well for Isabelle. You can subscribe and ask questions about any problem you might have, whether technical or with installation or anything. And usually people are very responsive and very helpful. So, and of course there's Stack Overflow that is very often used by the Isabelle community, where you can ask questions as well. I'd like to advertise a bit Larry Paulson's blog, Machine Logic, where he writes useful blog posts. Some contain general discussions on formalization of mathematics, others are can be helpful for beginners with examples about how to get started with Isabelle. And of course, Kevin Buzzard's blog about Lean, which I mentioned already a few times. So these are my conclusions from my own journey in formalization so far during Alexandria. So what we've learned within the project. So formalization, all the formalization goals were accomplished. So everything we set out to formalize, it worked. We have yet to encounter any material that was impossible to formalize in single type theory. We did run into some difficulties a couple of times, but there was always a hack to figure things out. So we have seen that advanced mathematics is also within reach. I gave a couple of examples already. Regarding Isabelle in particular, locales can be very useful to capture interaction between different mathematical areas. And sometimes I've used them to just include unformalized material as assumptions. You can see it as a bit cheating, but as long as you're transparent enough about what your assumptions are, it's fine. So to build on a famous theorem that might not have been formalized before. And sometimes the formalization process has revealed the need for a higher level of abstraction in prerequisites that we build on. Again, about Isabelle, Sledgehammer's automation is very, very helpful, at least for me. I have very positive feedback from students. They can learn Isabelle very fast and formalize advanced materials successfully. So both interns that I had from the mathematics department and students from the computer science department at Cambridge, they were all very, very enthusiastic and they did a brilliant job formalizing advanced material. It is really teamwork, right? So very often we've seen things that we lacked in prerequisites, and we know that somebody else was in the process of formalizing this material. So then, for example, in a recent entry, where we formalize material related to the polygonal number theorem with my students. We use some material that was recently formalized by another team. So it is collaborative work, keeping in touch with each other and filling whatever library gaps there might be out there. What we still need, we need better automation, we need efficient organization of the libraries, we need to manage the libraries in a way that is helpful for the users. The way we organize definitions, the way we develop elementary properties coming from the definitions and basics, and the way we build on formalizing more advanced results. And by working together efficiently, we can have amazing results, so our libraries can grow increasingly fast. So the main obstacles so far, yes, we need, like I mentioned before, we need better automation, we need better certs, organization, and readability of formal proofs by humans is another big issue. That this can be resolved in part by the way we also build our libraries and the way we choose to name our definitions and our variables and the comments we put in the code. Interoperability of proof systems is another big research question. So there's a lot of duplication of work done in various proof assistants. This can be interesting, of course, to compare how proofs can be formalized in different systems. But at the same time, there is also a lot of effort that is, a lot of work hours put into that. So it would be good if we translate automatically proofs between different systems. And this is one of the goals of the didactic system, which is being developed within a EuroProofNet project, which is a cost action. Okay, so where do we go from here? Conclude. So the future of mathematics is very hard to predict. We've seen a lot of recent developments coming from recent advances in AI. So we don't know which way things will go necessarily. This is an example, this is a paper from 2022. My colleague Wenta Lee was also involved in this paper, but as you can see, it attracted a lot of interest. Auto-formalization with large language models. So they developed an AI that can auto-formalize mathematics written in English and turn it into Isabelle code. This was another very influential paper from 2022, early 2022, by OpenAI, where they found that it was possible to solve, for this project they used the proof assistant Lean, it was possible to solve challenging problems, so they developed automation powerful enough to solve challenging enough problems drawn from high school Olympiads. This impressive work by DeepMind, it's not directly related to proof assistance, but it shows us how advances in AI could assist research mathematicians, right? So things are evolving very fast. So there is this very impressive work where AI could detect patterns that lead to conjectures for representation theory, right? This is the reference here. And there was, again, another related work by DeepMind for knot theory this time. They use AI to detect patterns to help generate conjectures in knot theory. So we can see for sure this is, of course, a huge text, calls for a lot of philosophical discussion, and it's a lot of food for thought, but the concept of mathematical proof is evolving. The way we, what we accept as a mathematical proof and how we think of a mathematical proof, it is evolving. So I would like to give this interesting recent reference, whether it's a discussion on that, the evolving notion of proof. And this is a collection of interviews that I did quite recently again on this topic. So what can formal systems do for mathematics? And many different points of view. So this is an extract that I really love from this wonderful, brilliant book by Francis Su from 2020, Mathematics from Human Flourishing. So he says mathematical exploration is very much like space exploration, but of a different kind of space, a space of ideas. You don't know what you find when you start. You send out probes, test theories, you are captivated by mystery, motivated by questions, undeterred by setbacks. You make discoveries from a distance because the ideas themselves are not physical, you access the space through reason. Exploration and understanding are at the heart of what it means to do mathematics. Exploration is a deep human desire and the mark of human flourishing. So, mathematics will always be a profoundly human activity. We're not working on proof assistants to suggest that they will at some point, or AI or combined with AI, they will replace mathematicians. No, that's not the point. Mathematics is a profoundly human activity. The joy of mathematics is inherent in humans. There is a human need. Yes, I'm finishing. It's the last slide. To do mathematics, I would not claim that every mathematical proof should be formalized to be acceptable. Mathematicians will always seek understanding. This is a hint at AI, let's say, generating proofs that might be incomprehensible to us or impossible to reproduce, which is not what we want. So the hope is to use interactive theorem proving to support and assist mathematical practice, right? Not to replace humans in that. And it looks like there is already a huge potential to do so. It is conceivable to substantially assist mathematicians with large collaborative projects, exactly because mathematical proofs can be big and complicated and they might need the help of many different authors. Proof assistants can also be used as a bookkeeping tool to keep track of everything and help with understanding and communicating between mathematicians. They can be used for bookkeeping, even for modern research level mathematics. One day in the near future, we might be using them for reviewing journal submissions faster. They can support literature research, and they can also be useful for education, trying to learn mathematics by using proof assistant and getting immediate feedback, right, by experimenting yourself. So that's all I had to say for today. Thank you very much.
Thank you. We have a couple of minutes left for questions. Are there any? Any questions in the room? Kevin looks like he has one.
So you mentioned large libraries maybe being useful for AI.
Yes.
But do you actually think I can never quite reconcile that with the fact that ChatGPT needed to look at the entire internet and AFP is 4 million lines of code? Aren't we sort of many orders of magnitude out for AI doing mathematics?
When I was thinking that I wasn't thinking of ChatGPT in particular, I was thinking of something more, let's say, targeted, let's say, to the libraries. It's better, but not the entire internet. So, yeah.
So not a large language
But, I mean, people were talking about that before, large language models, so this is kind of a shock.
That's okay.
Like, so it is conceivable because you write math code, so how can you make it more accessible to the computer to understand by using like mathematical code, not mathematical natural language. Now ChatGPT has changed this a lot, but I would imagine it would be easier for an AI to understand, in quotation marks, mathematics written in proof assistant compared to mathematics written in natural language. So they didn't have ChatGPT in mind when I was thinking of that, but this changes things a lot, of course. Yeah. Things are getting even more complicated, interesting. Yeah. With large language models. So, but there was this work that I mentioned, like when the collaborators that they had this tool that auto-formalized mathematics so you have mathematics as natural language as input and output is Isabelle code, so they have this working.
There was no large language model involved in that.
Well, you wouldn't, I don't know because there was a model, but it is sort of translating natural language to code in
Right.
an automatic way.
Which is what a large language model does, right? It's very good at translating,
Yes.
writing,
Oh,
right?
no.
But it wasn't a large, I don't know the word.
I don't know how you call it exactly.
But did they use the entire internet?
No, I think it was specific data set that they use, but maybe you
Are they still doing something?
No,
You said there was state of the art on mini F2F,
yes.
and that's certainly something.
I think this was material that had to do with high school, mathematics in India, I think.
Right. A lot of people, it seems to me in this area that a lot of people are sort of stuck on the high school level.
Mm-hmm.
I don't know how difficult it would be to get.
Yeah, I guess it's a huge difference in difficulty, right? But things are evolving very fast, so who knows in a few years.
Fair enough.
Do we have any other questions? Anything from the online chat? So I think some conversation is going to continue. Oh yeah, there's a question. Yes, please.
Thank you for your presentation. As you can imagine, I couldn't be more of a fan of Isabelle, and so very excited about the program. But you've made some assertions there that I think that could be valuable for the community to investigate further. You say that your students found it easy to learn. And indeed, Jim here teaches Isabelle at undergraduate level, so it is easy at some point, in some sense. But I found also that people can take quite a lot of time. There is a steep learning curve to get to Isabelle. And so I think it will be interesting to think about what could be done to lower that curve. Mm-hmm. And one thing that I found very interesting is the challenge that you put at the beginning, that we start helping people to discover proofs. And another anecdotal experience that I have with my colleagues and so on is that Isabelle does not help them to find proofs. It helps them to make sure that their proofs is all right.
Absolutely, yeah, absolutely. I was thinking in the far distant future where you could use this code assisted with AI, and it opens the door to a lot of potential future tools, but not at the moment. Absolutely not at the moment. It was a future goal, yeah.
Okay.
Maybe using it as, let's say, a tool for literature search. If you have material formalized, it can maybe locate it more easily and help you in that sense, or maybe provide counter examples. Oh, you're trying to prove this. Here is a counter example to what you're trying to prove, based on maybe some literature result that is already out there. Mm-hmm. So yeah, it was a vision for the distant future, not right now.
A nice challenge.
No, it depends on many things, how things go. But back to your remark about learning Isabelle. So the way I learned it, and I think it's useful. I mean, it's when you have a challenge to formalize. So when you start learning it from tutorials and online manuals, it doesn't work so well. So I think it works best when you have, and we were talking about that during the coffee break, that it works best when you have a challenge. I want to formalize this theorem, and then it's learning by doing. I think this helps a lot. So I haven't taught Isabelle to students, but we have done projects together. So I always give, here is the end goal. We want to formalize this material. And then we go on and learn by trying to solve problems.
I think that's exactly right.
Yes.
We have a version of our course which we teach in industry.
Mm-hmm.
And problem-based learning at the end of the course is exactly the right kind of thing.
Yeah.
A problem that they're really committed to finding a solution to, and then they want to do it.